Okay, no questions about the assignment then. So one thing I'll say though is that make sure to go to Gradescope and set up your account on it soon. Don't leave this kind of thing until close to the due date. You might just find that there's something that you don't get, or you make a mistake and you don't have time to fix it and stuff like that. So make sure that you're set up on that and ready to go sometime the next day or two. Even if you haven't started your assignment yet, just get set up on Gradescope. Gradescope is where you're going to submit assignments. You're also going to submit your midterm and your final exam when you take them onto Gradescope as well for grading. It's much more convenient for me to grade your work on Gradescope because I can grade it question by question for everybody, not one person's test at a time. So it means if I use Gradescope, it means that it's way easier to mark you all to the same standard. Okay. So make sure you get on that and you get set up on Gradescope. Did I stop sharing? Sorry about that. I'm not using the iPad this time because I don't have it. So I'm trying to use my laptop. Yeah. Okay. Yeah, so make sure you go into Gradescope, click around and get used to it. Also, start the assignment as soon as possible once it's posted. There's going to be 10 questions on it. They're going to be a little harder than the quizzes, especially the first quiz. That was an easy one. Just the questions might be a little longer, a little more tricky because you have all week to do it instead of just a half an hour. So make sure that you get started on it early and that you're not rushing to get it done at the last minute. There is a late penalty for people that submit the assignment late. I want to keep everybody on the same schedule here because I want to be able to post solutions for you after the deadline date, so that you can read the solutions and know where you went wrong before your test, which is the end of next week. So I can't really be waiting on people that are late in handing in assignments. There's late penalties that apply, and if it's too late, I have to check the course outline to remember the details. You'll just get 0. So make sure that you're on time with it. No questions about Gradescope so far? Everyone read the email, the announcement, and has a good enough idea of how it's going to work? Okay, thanks, Isn't. Okay, so we ended on domain last time, and I'm going to run through one more example of finding the domain of a more complicated function. So what I'm actually going to do is get you to find the domain yourself of this one and see is it the same thing that I got. So you should have been practicing your domain last week in advance of the quiz. So I'm hoping that you're not too bad at this. It's a little more complicated than the ones we covered last week. It kind of mixes a few functions together into one function to make kind of a bigger function, and the domain is a little more hard to calculate here. Right, so there's just a few things you have to remember at once. So what I want you to do right now is to, oops, sorry, I have a mistake in the way I've written it. X squared minus 1. So what I want you to do is give this one a try and try to find the domain. And I'm going to pause here for maybe 3 or 4 minutes to see if you can write down the domain for this one. And then I will go through the solution. And if you got something different to what I got, try to take a minute to understand where you went wrong. Or if you think I've gone wrong, then raise it with me too. Everyone makes mistakes. I might get it wrong too. So give it a try, and I will catch up with you in 3 or 4 minutes and do it myself. And in the meantime, if you have any other questions about quiz or assignment or whatever, grade scope, whatever it might be, you can just pop it in the chat right now too. Okay, so this one's a little complicated. You should be running through this one kind of piece by piece. The root 3 minus x, the root x squared minus 1, and the x plus 5. And kind of bringing it all back together and saying, okay, what's allowed in this function and not allowed, what's allowed in that one and not allowed, what's allowed and not allowed in the last one, and putting it all together and saying that you can only have something that's allowed in all three pieces. Maximus, you do have a quiz on the Friday as well. It'll be on similar content to some of your assignment questions anyway. So as you're working through your assignment, you will be practicing for your quiz anyway, as long as you get started this week. Two birds with the one stone. Quizzes every week except for the weeks of midterm and final. Okay, is anybody finished or thinks they might have the answer yet? No one sure? It's a little longer, this one. Okay, let's go through it piece by piece. Piece by piece. Okay, so let's say we look at the root 3 minus x. What numbers are allowed or not allowed in this? So I'm going to kind of write this in English rather than write domains first, because we want to just get a sense for all of it, and then we're going to put it all together afterwards, okay? So what do we need for numbers to be okay in that part of the function, the square root of 3 minus x? Well, if numbers get bigger than 3, that's a problem, because 3 minus 4, 3 minus 5, they all lead to negative numbers, even 3 minus 3.001. That would still lead to a negative number, and you can't have a square root under the negative. So when I look at this, I think that I can't have numbers greater than 3. No worries, Minoja. I think that does ring a bell about your email. I've got a lot of emails last week, so I can't remember exactly, but that's okay. Was it your first or your second vaccine? Second vaccine, yeah. I had my second one a few weeks ago, and I got Moderna for both of them. For the first jab, I felt nothing, no symptoms, nothing like that. And the second one, I got some symptoms. I couldn't sleep. I had a fever that night, and I couldn't sleep, but it passed pretty quickly. So you can feel pretty miserable by the time nighttime comes tonight, maybe, if it were, or you might feel nothing. You might be lucky, but it doesn't. The symptoms don't really last long if you get any. So you might not be able to sleep or have a fever or something like that, but it goes away pretty quickly as well. Oh yeah, what we're talking about. So looking at the piece root 3 minus x, when I look at that, I say, okay, I can't have numbers greater than 3. Going back to the function, numbers bigger than 3 might work in the square root of x squared minus 1. They might work in the x plus 5 part. But because they don't work in the root 3 minus x part, they can't work in the function as a whole. So when I look at this one, I'm not so much thinking about what's allowed, I'm thinking about what's not allowed. Because if something is not allowed in one piece of the function, it's not allowed in any of the function. So my approach here is what is not allowed. And then I'm going to see what gets ruled out from every piece and see what I'm left with. That's going to be my approach here. Okay, so we also have the square root of x squared minus 1. Again, we have another square root problem. We have x squared minus 1 inside the square root. Again, we're concerned about it being negative inside there. And when is it going to be negative? That would be when x squared is less than 1. And that is going to happen when x is between negative 1 and 1. Eric has an answer. Let me see if that one works. I think that's correct, Eric. I think you're correct. I'll catch up with you soon, and you'll see the thought process. And I'm pretty sure I'm going to end up with that answer. But I think you're right. Good job on that one. Okay, so where was I? Yeah, so you can't have numbers between negative 1 and 1 because those would lead to a negative number inside the square root. Can't have numbers between minus 1 and plus 1. Now, the numbers minus 1 and plus 1 themselves, in this part at least, are okay. As Eric has in his answer there, he has the hard brackets around minus 1 and 1, because this for 1 and minus 1, x squared minus 1 is equal to 0, and the square root of 0 is just equal to 0. That's defined. If that was in the numerator, sorry, in the denominator, that would be a problem. In the numerator, the endpoints are okay. And then the last one, for the x plus 5 part, this is in the denominator. So we can't have x equals negative 5 because that would cause the denominator to be equal to 0. And you'll notice in Eric's answer as well, he has the soft brackets around minus 5, meaning that minus 5 is ruled out. So he has everything from negative infinity all the way to minus 5, but the soft bracket around minus 5, the curved bracket, means that you don't include that endpoint. Okay, so one way to do this then is to draw a number line like this. And let's mark in some of the key points that we thought about here. There was a minus 1, a 1, a 3, and a minus 5. These are some of the key points, right? Now we can't have a minus 5. So that one can't be in there. Maybe I should go a different color here. That one can't be in here. We said that we can't have numbers between minus 1 and 1. So we're going to rule this out. I'm going to color in some red here. But minus 1 and 1 themselves are okay. We also said that we couldn't have numbers bigger than 3. So this here gets ruled out as well. I think that we said that we could have 3. 3 was okay, but everything after 3 is not okay. So I'm going to put, whoops, I'm going to go back to black here. I'm going to put a filled in dot like this around 3 because I want to remind myself that I want to use the hard bracket. And I've kind of used 2 notations on top of each other here for this one. That's supposed to be a not filled in black circle, meaning that the 5 is not going to be allowed. And I also have put a red cross through it. So let's see what's allowed. This here is minus infinity to minus 5. This part here is minus 5 to minus 1, and that's a hard bracket. I'm not going to talk about that part. And this part here is 1 to 3. So what I'm thinking as I look at this is that these parts here they are allowed in the function. So our final solution then, the domain, is minus infinity to minus 5, minus 5 to minus 1, 1 to 3. We're not including that middle bit. And yeah, that's what Eric had as well. So just one final check to see if it was the same answer. Okay. Any questions about that one? A little harder domain problem. So as you would have seen on your quiz, a little bit easier on the quiz. And they're going to get a bit harder in an assignment like that because you have plenty of time to figure it out. Any questions? Okay, so go ahead, Lewis. Hope this is working. What were we supposed to do when it asked to simplify in the radical expressions? So remember the rules for simplifying radicals. You can't have a square root in the denominator. You can't have a fraction under the square root. And you can't have any square factors. So if there's a factor of 16 or something, you'd have to extract that as a 4. So when you run through your operations, you end up with something that looks like I think in the question that I gave you, it was in the form a root b over c once you've run through the simplification process. So it you had to select what a, b, and c would have to be. I actually don't remember the question. If you can remember it, I can run through it really quickly here. Whichever one you got, you would have got different questions from other people, so I can't post solutions. There'll just be too many. But if you can remember the question, or if you like, Lewis, email me about it after class, and I can help you with it. And we'll just keep going here. I think that might be better. Yeah. So if you're not sure, we can talk about it by email or another appointment. Okay, where were we? So we covered another domain problem, and there was one last point I wanted to make on domain before we can move on. Wait, no, I have to cover inverses first because it's about the domain and range of inverse functions. Okay, so moving on to inverse functions now then, and we're going to revisit domain and range very soon. Okay, so I hope most of you have kind of a loose understanding of what an inverse function is to begin with. What we're going to be doing in this course is just being able to identify when a function has an inverse, being able to draw a function's inverse if you're given the graph of a given function, and also calculating the inverse using algebra and steps like this to a given function. So just before we start, in a nutshell, in a few English words about what an inverse is. If you have a function that sends, let's say, 3 to 7 and 4 to 9 or something like this, then your inverse function should send 9 back to 4, 7 back to 3, and so on. An inverse function does the reverse of what the function does. For example, a basic one might be, if you have a number that squares all the numbers, then the inverse function would take the square root to go back again. If you have a function that adds 10 to every number, the inverse function would subtract 10 so that you go back to where you started, kind of. So let's say an inverse, let's say the function is just x plus 10, so it takes a number x and adds 10 to it to give you a new number. So 11 becomes 21, 12 becomes 22. Then the inverse function is going to be x minus 10. So 21 becomes 11, 22 becomes 12, and so on. So it's just a number that kind of reverses what happened in the original function. So yeah, there's a few examples of that here. Now, one thing to note is that not every function has an inverse function, and there's a way to check if a function does or not. So the rule is, it's about whether or not the function is one-to-one. Now, can you put a yes in the chat for me if you covered one-to-one in high school? Didn't. Okay. Okay, because I went to school in Ireland, obviously, and I didn't. I had a different curriculum to you guys, so every so often I'm gonna have to just check if you did something, because it's easier to know what's exactly in the high school course when you've gone through it yourself. So one-to-one, well, the definition is right here. It's a function is one-to-one if for every range element there is only one domain element. Now, this might be kind of ringing a bell to something that we did in the last class. It was, remember when we defined a function? It was a relation is a function if it follows this rule that for every one domain element, there's only one possible range element. This one is going one step further, and it's saying, okay, not only, so a function has an inverse if for every range element there's only one domain element. And last time I was talking about the function x squared, I was saying, well, you know, we're thinking of these functions and we're talking about one range for one domain, but we never said there only had to be one domain for one range. And I gave the example that in the function x squared, if the range element is 4, there were two possible domain elements. It could have been 2 squared, or it could have been negative 2 squared that got you to 4. So you have 2 and 4, and also negative 2 and 4 as kind of pairs, as things that exist in the function. Now that is absolutely fine for a function. A relation that has, say, 2 and 4 and also negative 2 and 4, that's a-okay as a function, but it is not a one-to-one function, because there is a range element, there's many range elements, 4 is an example of one of them, but there is not just one domain element, there's 2 associated domain elements with it. So although x squared is a function, it's not a one-to-one function, okay? And the reason that I'm talking about one-to-one, I know we started talking about inverse functions, and all of a sudden I'm like, you know what one-to-one is, here's what one-to-one is. The reason that I'm talking about one-to-one is because that's how you know if a function has an inverse or not. Only functions that are one-to-one functions have inverse functions. So x squared does just x squared without introducing anything else. Just if I just say, does x squared have an inverse function? No is the answer. Now, what we do sometimes is we restrict the domain a little bit so that you can give it an inverse function. But just as is, x squared doesn't have an inverse function. Any questions so far about that? That's something new. It might be a little awkward. So earlier I mentioned the square root of x kind of reversing the operation of x squared. Now, I'll get to restricted domains in a second, But you'll notice that if you take the square root of 4, you never say it's -2, you always say it's +2. So you kind of just take one possible domain element for the given range element. So what we say is that x squared only has a one-to-one function if only has an inverse for a certain restriction on the domain. Yeah, can do. So it's right here. For some reason I can't highlight this, but a function is one-to-one if for every range element there is only one domain element. So what I'm going to do is maybe draw it a little bit. I'm going to stop presenting here, and let's do a window over here. 1 second. Hide. Okay, so the key part of the definition is that for every range element there is one and only one domain element. So for example, let's say we have a function that is doing this. Let's say 5 is being sent to 7, 4 is being sent to 6, 3 is being sent to 5. Let's say you have it like that. So that one is one-to-one. So far anyway, we haven't found any evidence that there is a range element that has two domain elements. And let's say the function is, it looks like it's x plus 2, right? You're taking a number on this side over here and adding 2 to get the new number. So the domain element, you take any domain element, add 2 to get the range element. Okay. Now, what if we looked at another function that did this? Let's say we looked at a function where you have 2 and also -2. And let's say 2 gets sent to 4, but -2 also gets sent to 4. This is not one-to-one. And for example, this is a function like x squared, because the range element 4 has two possible domain elements. It can be 2 or it can be -2. But for every range element over here, for 7, the only corresponding domain element is 5. For 6, the only corresponding domain element is 4. And for 5, the only corresponding domain element is 3. So that one follows the rule. For every range element, there's only one domain element. But this one over here, that doesn't follow the rule, because for the range element 4, there's two possible domain elements, 2 and -2. Okay. Okay, I hope that one helps. We'll be talking about this more anyway. There's also a horizontal line test to test for one-to-oneness as well. So we'll be doing it more. Thanks, Waheen, or Waji. Okay. No. Okay, so going back over here. See, as I mentioned, the reason that one-to-one functions are important is because only functions that are one-to-one have inverses. Oh, you did do this, Alexi. Was it called something different? Maybe other than one-to-one?
No, it was called one-to-one. I just remembered because I haven't done this in like a year because I took all my maths in grade 11. So.
Right. Yes, sometimes it's called injective, I think, is one-to-one, or is it surjective? There are other names for them too, but I actually forget now because I think in Canada they just call it one-to-one. So I forgot the other names. Okay, so a way to test if a function is one-to-one is with something called the horizontal line test. Now this might also be kind of ringing a bell, because last week we talked about a vertical line test to test if a function is actually a function. And that's really all we're doing with the horizontal line test. Is we're trying to test, is the graph of the inverse actually a function? It's kind of the other way around. So horizontal line test, the function is 1 to 1 if and only if any horizontal line intersects the curve at most once. So looking at two examples of graphs here, for the very first one, the first one in that graph, that is 1 to 1 because anywhere that you try to draw a horizontal line, you will only cut that graph one time. But if you look at the second one there, that one is not 1 to 1 because, for example, if you drew the horizontal the horizontal line y equals 1, that's going to cut that graph a bunch of times. So actually, I'm going to go back to my writing here for a second, just because I want to illustrate that a little more, what that means. This again is just another way to think about domain and range elements, except this time it's in a graphical form. So for example, let's say I have some function doing this. So another way to interpret domain and range, you can think of domain as, so I should say, think of domain as x-axis elements and range as the corresponding y-axis elements. So now if I try the horizontal line test, let's see some pairs that are in here. Whoops. How do we go back? There it is. Let's say I draw a horizontal line like this. Okay. It fails the horizontal line test because it cuts the graph 3 times. I can find a horizontal line that cuts it 3 times. And let me just throw in some numbers here. Let's say this was 1, this is 2, and this looks like maybe 3.5, I guess. And let's say this horizontal line is the line y equals 2. This point here would be 1, 2. This point here would be 2, 2. And this point here would be 3.5 and 2. Okay? Failing this horizontal line test, this tells you the exact same thing that I mentioned in that definition earlier. That was about, in order for a function to be 1 to 1, remember, you needed for every range element, there needs to be one and only one domain element. Well, that doesn't happen here, and it fails the horizontal line test in this way, because for the range element 2, you have 1, you have 2, and you have 3.5 as corresponding domain elements. So it fails the one-to-one test because it fails a horizontal line test. See the connection between the definition and this horizontal line test now? For the range element 2, we have corresponding domain elements 1, 2, and 3.5. Therefore, it fails horizontal. Okay, that's not why it fails the horizontal line test. Therefore, it is not 1 to 1. I mean, clearly it fails the horizontal line test. It fails it because it cut the curve in a couple of places. So what I'll say is that this fails the horizontal line test. And failing the horizontal line test means that it's not 1 to 1, because when it fails the horizontal line test, it means that there's multiple places where there's a range element with different domain elements like that. Yeah. Are there any questions here? That make sense? So we haven't even tried to find an inverse yet. We haven't really talked about it much except for the very start. We're still just talking about when a function has an inverse and when it doesn't. So this is kind of the background that comes a little bit before inverses. Okay. And let me go one step further here and say, okay, so as I mentioned, a function needs to pass the horizontal line test and it needs to be one-to-one in order for an inverse to exist. Functions need to be one-to-one to have an inverse. Because as I said earlier, if a function sends one number to another number, then the inverse function should send the other number back to the original number. So the function above, the one that I've drawn, sends 1 to 2. It also sent 2 to 2. And it sent 3.5 to 2 as well. Let me just move that 2 down a little bit. But how would an inverse work? Where would the inverse inverse function send 2? Would 2 go to 1? Would 2 go to 2? Or would 2 go to 3.5? Because if you remember, the first rule that we talked about for a function is that for any one domain element, there needs to be, for any domain element, there needs to be one and only one range element. Well, this won't work. You can't have 2 being sent to 3 different places. So the inverse function fails the rule that you need for it to be a function, meaning that the inverse can't exist. You follow? So recall, can't have a function having more than one range element or a domain element. So here's something as well that you need to think about when we're doing this. Let's say we have a set over here that has the numbers 1, 2, 3, and we have a set over here that has the numbers 11, 12, and 13. If you have a function f of x, then f considers this the domain and this the range, because that's the numbers you start with, the ones that you kind of put into the function. That's the domain, and the numbers that you get back out, that's the range. But if you have an inverse function, let's say you have an f inverse of x, well, that's sending this over here. And as far as the inverse is concerned, this is the domain and this is the range. So a problem would be if you had, say, 2 and 3 both being sent to 12. That f of x is a function because you can do that with f of x. You can have the same two. You can have 2 different domain elements that get sent to the same range element. But if it was to try to work the other way, so if you're talking about 12 going back the other way, you can't have, now 12 is the domain and 2 and 3 are the range as far as f inverse would be concerned. So you can't have 12 having 2 and 3 both as range elements. So the only way it works so that an inverse exists is if you have something like this. be posted later. I haven't decided if I was going to post these or not. Do you think it would be helpful for it to be posted? Would you actually watch it again, or you'd really watch it? Okay. I just never believed that people would rewatch them. Okay, I can post them then. Okay. Any questions while we're at it right now, though? Yeah, these are long videos, so it takes a long time to upload it to YouTube and then to get it set up. So I thought that if nobody had watched it, I just wasn't going to bother. Yeah. Are we following? Any questions? Are we sure we have no questions? Maximus, you're asking, was it going to be recorded? I wonder, does that mean you're a little unsteady here? Okay, so let me head back to the textbook just to make sure I don't skip anything. We should have just about covered when a function has an inverse. I don't think there's too much more to say now apart from a few little notes. So how do we actually find it? Okay, graphically is not something that we're going to do very much, but one way to find the inverse function given with a given function f of x is to draw the line y equals x, as you can see here. Now, if you start with this function here, the red line, if you imagine reflecting that, if you imagine going like straight through this line y equals x and then the same distance again at every point and drawing the reflection of it through that line, if this original function f of x has an inverse, then the graph of the inverse function will be its reflection through the line y equals x. That's more just kind of an interesting observation. It might be an exercise I get you to do actually in a quiz or something. I might just say, if this is a function, what would its inverse look like? And give you a couple of options as pictures. But it's not really something that you'll use in practice that much, I think. It kind of comes from the idea of the inverse function kind of takes all the ranges become the domains and the domains become the ranges, and the reflection through y equals x sort of reverses that. It turns a domain into a range and a range into a domain. I'm going to let you think about that a little bit and see if you can sort of sort it in your head and make sure it makes sense. But as an example here, let's say you reflected, actually I think I'm going to need to draw again in order to talk about that. So let's say we're talking about, oh, maybe I won't use that pen. Reflecting a function through the line y equals x, thinking about the inverse. We kind of talked about how when you go from a function to its inverse, the domain and the range kind of get flipped about, right? So back up here, for example, 1 for f of x, 1 is the domain and 11 is the range. For f inverse of x, 11 is the domain and 1 is the range. So let's just look at what happens if we were to reflect. Let's say we take that, something that looks like that one there. This would be the reflection of it, right? So let's say we had this number here. It was, I'm going to maybe need a different color, 1 and 3. So that would be the point 1, 3. If you reflect this through here, well, the point that you actually get is 3, 1. See how the domain became the range and the range became the domain? This, for the original function f of x, this one's f inverse of x, 1 was a domain element and 3 was a corresponding range element. But for f inverse of x, with that reflection, 3 is a domain element and 1 is a range element. See what I'm getting at? A little tricky, I know. Just something to think about for the reflections through that line y equals x. If you like, you can think about, will that happen every time you reflect through the line y equals x? Will that always happen? Why will it always happen? A little hard to think about, but kind of a good exercise. That's really what mathematics is, really. It's you pick at stuff and you try to say, is that always true? Like, why would that always be true? So something to think about. I'm not going to examine you on something that tricky, but something interesting to think about, I think. Okay, so coming back over here. That was one way to think about inverses. It was graphically. I'm going to have to speed up here. But what we're going to be doing mostly is algebraically. I'm going to say, here's f of x, find me f inverse of x. And in the book here, I've written you 4 steps that you can follow. So if I give you like f of x equals 3x plus 2, start off by replacing the f of x with a y and call it y equals 3x plus 2. Then rearrange to get the x isolated. So bring the 2 across and divide by 3 so that you have x equals something. And then you pretty much have the answer then. Interchange the variables x and y. Again, the domain becomes the range and the range becomes the domain when you go into inverse. And then rewrite as f inverse as your final answer. So yeah, with 3x plus 2, bring the 2 across, divide by 3. So now you have x equals y minus 2 over 3. Interchanging x and y, because what you're trying to do is say, okay, now I want the domain, I want x to be my range and y to be my domain. I'm going to swap the names of the variables and rewrite with f inverse instead. So f inverse of x would be x minus 2 over 3. The calculation part is not the hardest. You're just going to have to remember what to do. I'm sure everybody here can bring a 2 across and divide by 3, swap the x's and the y's, and then rewrite the answer. And that's probably what I'm going to be asking you to do for the most part. Or at least it's the most important skill. I might ask you something about the graphs on the quiz, or even on the midterm. I've already made the assignment, and I don't think I've done that on the assignment, have I? I can't remember. But you'll see that soon enough anyway. Okay, so here's another one, and here's something that I was talking about domain restrictions. Find the inverse of f of x equals 2x squared plus 3, where x is less than or equal to 0. Now, the first thing to note here is that, and to be honest, I did kind of skip this step here before. We said, let's find the inverse of this function f of x equals 3x plus 2. Really, I guess what I should have written in here was, does an inverse definitely exist? Let's just try to verify somehow that that the horizontal line test is passed and that the function is one-to-one. So I hope that most of you know what that function looks like. If you were to draw y equals 3x plus 2, I hope that most of you are thinking, oh, that'll be a straight line. Because that's the equation of a line. Y equals mx plus b. M is the slope, would be 3, and b would be the y-intercept, would be 2. I would just draw a line that's kind of diagonal like that, kind of steep, because the slope of 3 makes a pretty steep line. And if you draw a horizontal line anywhere across there, it's only going to touch it once. So it will definitely pass a horizontal line test, and therefore it will be one-to-one. So that's something that you can bank on, and then you can proceed and find the inverse. So yeah, in practice, I guess you do have to just think for a second and say, is that definitely one-to-one before you start? And if it turns out it's not one-to-one, you might say, hey, that function's not one-to-one, so I can't have an inverse. And that might be your final answer. Here I'm just trying to run through the steps, I think. So, okay, on that note, going back to 2x squared plus 3. If you look at the graph of 2x squared plus 3, it looks like this here. Now, an alarm bell should be ringing in your head saying, that is not one-to-one, because if I draw a horizontal line the way my mouse is going here, that's going to cut the graph more than once. It fails the horizontal line test, meaning that there are range elements that have multiple domain elements. It's not one-to-one. So maybe I can't do the question because there should be no inverse. But be careful, because if you go back to the question, you'll notice that there is a restriction on the x's. Find the inverse of 2x squared plus 3, where x is less than or equal to 0 only. So with that restriction, this is actually the graph that you have. And that's what you're going to see from me from time to time, is when I don't want to use the most basic function ever for you to do something with, I might use a function that will lead to a little bit more algebra to do, but I will either put a domain restriction or I won't. Chances are I've meant to put a domain restriction and I might forget. And if that happens, I guess you get lucky and you can say, this one's not one-to-one, so there is no inverse. And then I go, damn it, I guess I have to give you full marks for that. So yeah, watch out for the domain restrictions and be aware of what they're going to do to the graph, whether it will actually make the function one-to-one or not. If this restriction as well, if that was x less than or equal to 2 or something, then it would fail the horizontal line test. Because if you look at 2, the graph would go as far as, I don't know, 7 or something, or 8, and it would still fail the horizontal line test. So just be aware of what the restriction is doing. With this restriction, the function does pass the horizontal line test, so an inverse exists, and then we will run through the calculations. So I'm just noticing the question, how would the restriction affect the equation? And how would we find the inverse in that case? Oh, yes. So we're about to do that now. So the inverse, it doesn't really affect the equation except for one place at the end, which is this line right here. So if you're specifically thinking about that question, just get ready for this line here where I talk about it, and in the paragraph. So running through the calculation here, what did we want to do? Well, it started off by saying if you see f of x anywhere, change that to y for convenience, and then try to get the x on its own. So again, we're going to bring the 3 across, so we have y minus 3 equals 2x squared. In order to get x on its own, we don't want that 2 there, so we divide across by 2. And now we have x squared equals y minus 3 over 2. So for this to work, x could be negative root y minus 3 over 2, or x could be positive root y minus 3 over 2, because either of those things squared will get us back to y minus 3 over 2. Now, here's where the restriction comes in. How do we decide which of these is the answer? Because we're starting to look at something that would lead to this problem of it not being one-to-one. We might have two different range elements for a domain element. Which one is the right one? Well, what we're going to have to do is select the right answer here based on the restriction that we're given. So before proceeding with the interchanging of variables, is it x equals this or x equals that? To decide, you look at the restriction. The question stated that x was less than or equal to 0, so the negative option was the right one. So we're going to select that one and go from there. We interchange the variables and we rewrite it as f inverse equals minus root x minus 3 over 2. So we found the inverse function. Now going back up, you might notice that this would also work just fine if this condition was originally x greater than or equal to 0. We would have the right side of this graph here, not the left side. And if that was greater than or equal to 0, when we come to this part here, we would say, oh, well, it can't be this one. It has to be the positive version. So our inverse would be the other answer. Why is it either plus or minus? Oh, okay, so going back up, let me share a different screen. No, it's okay to ask a basic question. Don't worry about that. Find out. Like that. So at this point here, we had x squared equals y minus 3 over 2. It's like, okay, we have y minus 3 over 2 and that's awkward. It's like if I asked you if x squared equals 4, what are the possible options? I can have x equals minus 2 or I can have x equals 2. So what I'm kind of doing in my head is I'm saying the square root of 4 equals 2. But if I'm trying to solve, I know that it doesn't matter if it's plus 2 or minus 2. Either of those things squared will get me x squared equals 4. So in the same way, what I'm looking at this is I'm thinking, okay, I'm going to have root y minus 3 over 2. But I know that I can have minus root y minus 3 over 2 or plus root y minus 3 over 2. Because if I try to go back to the step above, x squared sorry, I've drawn a bad square root there. Because in the same way, minus 2 squared and x equals 2 squared both give me 4 from the original question. Make sense? Okay. Stop presenting. I'm going to run back to the textbook again for a second. So we're about to just do some problems in, finding the inverse, given this, find that. And then we'll be moving on from inverses. We have a good bit more to do today. So the last important thing to note about this section on inverses is about the domain and range. I did mention this a few times. We talked about how, as far as the inverse function is concerned, the range is the domain, and the domain is the range. So here it is again, just one more time. The domain of f of x is equal to the range of f inverse, and the range of f of x is equal to the domain of f inverse. Now, I haven't talked about range all that much. Range can be kind of hard to calculate sometimes. For the domain, when I ask you to solve the domain of a problem, it's sort of straightforward in that you kind of look at the function and say, these numbers won't work because it'll lead me to square roots of negative numbers dividing by 0, other undefined things. You can kind of look at it and say, that won't work, that won't work, that won't work. But to try to find a range, you're looking at a function and going, what are all the possibilities that it can be? You're like, well, I kind of have to think about every number and try to imagine a trend and try to find the lowest point and the highest point or something. If anybody's done calculus before, when I mentioned lowest and highest points, you might be thinking, hey, maybe differentiation might help. I might be able to locate those places and find the range. We're not actually going to go into calculus in this course because you're going to get enough of that in university anyway, so I really just want to run over the background before calculus. But one thing that you might do if you're trying to find out the range of a function f of x is use that fact to say the range of f of x is the domain of f inverse. So I'm going to take f of x, find f inverse if it exists, and then the domain of that is equal to the range that I'm looking for. So that can be useful because you can use that fact to find ranges. You have other ways to find ranges too, and calculus might come into it, but I'm not going to ask you too much about range in this course. I'm going to stick mainly to domain because it's kind of the more important one, and we don't really have all the tools to tackle a wide range of range problems, a lot of different range problems. So yeah, I'm going to stay away from range a little bit. Okay, so some exercises here that we can go through about domain and range. I'm going to leave these for you guys to practice, I think. And I have a few different ones here. So once I get through one or two problems here, I think we'll take a little break. My voice is already starting to crack a bit. I'm not even halfway through class. Okay, so some more examples of the mechanics of finding, hey, this isn't, can you see my screen? It's not working for me right now. You can see the OneNote, the example that I just wrote? Oh, I can't, that's weird. It just is a black screen for me where I would see where it's normally sharing. Okay, well, I'll keep going. Okay, so let's say our question is find f inverse of x if, let's say 1, f of x is root 2x minus 1, and 2, let's say f of x is x plus 1 over 3 minus x. Okay. Now I'm actually going to stop and reshare because if it bugs out or something, I want to be able to see it. Yeah, it's working now. Weird. Okay, so starting with question 1. F of x is root 2x minus 1. Okay, so actually later in this class we're going to be talking about the graphs of functions. This one, I guess for now you'll have to trust me, it is one-to-one. It looks something like that. It's a root function. But it is one-to-one. It's going to pass the horizontal line test. And yeah, I guess for now, just take my word for it that it is one-to-one. So an inverse exists. So what do we do to find it? Well, the first step was to say, okay, let us replace any f of x that we see in there with a y. Now, the next step in this process is to try to do whatever we have to do to turn this into the form, not y equals function of x, but x equals function of y. So we want to get the x on its own. Any suggestions for how we're going to start here? What would you do if you were trying to get x on its own? Take the root. Take out the root, yes, yeah. So, and how would you get rid of that root? What would you do? You don't want the root there. That's the first thing that I'm thinking too, is that I don't want that root right there. I'd want the x freed away from that. Yeah, square. Yeah, I see people saying square. I know that it's just a bit awkward to say it. But just be careful. If you square one side, you also have to square the other. It's not just the 2x minus 1 part that you're squaring. It's going to be everything. So you're going to have y squared equals 2x minus 1. That works. Okay, I want that x on its own. So next thing I'm looking at is that, well, I don't want that 1 on this side of the equation beside it. I'm going to bring that across. And then finally, I don't want 2x equals something, I want x equals something. So I will divide across by 2, and I'm just going to rearrange the equation. I'm going to bring them to the other sides. It's going to be y squared minus 1 over 2. Yes, sorry, it should be a plus 1. When I bring that across, it should be a plus 1, thanks. And I should change it here too. Okay. So that looks good. We're going to interchange. Because again, we want the range and the domain to be switched. So y is going to be x squared plus 1 over 2. And finally, that is our inverse. F inverse of x equals x squared plus 1 over 2. So the mechanics of this are simple enough. I mean, I don't think I need to spend too much time going over some basic operations like bringing 1 across, dividing by 2, and so on. This is why I talk so much about the what's going on in the background and what things mean and reasons for things. Because this kind of practice, you should be, for every one of these problems I do in class, you should be doing 5 or 6 of them in practice, just to make sure that you're good with all the mechanics. But that's something you can do yourself. So the other problem that we're going to do is x plus 1 over 3 minus x. F of x is x plus 1 over 3 minus x. Okay, so again, the first step that you should be thinking of is, let's use y, because it's more convenient to have a y going around in the equation than an f of x. What would you do now? You want to get the x on its own somehow, but there's 2 x's in there. You might not know exactly where it's going to go, but does anybody have a suggestion for the first step? No one has an instinct about maybe how you might start this one? Yes, that's very good. Multiply it by 3 minus x. So both sides of the equation are going to get multiplied by 3 minus x. The reason that stands out to me is because I don't really like to see denominators in there. Oh, this might be more awkward than I meant. My bad, I'm being an idiot. Let me fix the right hand side. We had 3 minus x multiplied by x plus 1 over 3 minus x. Okay, so when we do that, the 3 minus x is going to cancel, and we're just going to have 3 minus x times y equals x plus 1. Now, the reason that I wanted to take that step is because, just like in the last problem, when we started off, we were thinking, okay, what feels like an obstacle to making this work out? I didn't like the square root, and someone suggested square on both sides. I'm thinking, yeah, I don't want that square root interfering with me getting at the x. So let's do something about that. That one here, I'm looking at this one thinking, I don't like that it's a fraction, because I can't really get the x. I can't really add those x's or combine them somehow in that fraction form. So what do I do to make that easier to work with? I multiply across by the denominator, so that now I just have a bunch of x's in the numerator. And I'm guessing the reason that you said, multiply by 3 minus x is because once you've done that, you can maybe get the x's on one side and get the rest on the other side and factor out and divide and stuff. So you're thinking it's just easier to try to get x on its own in that way. So you're kind of looking at maybe what looks like an obstacle that I want to try and sort out. Okay, so multiplying out here, we have 3y minus 3x equals x plus 1. Again, I don't like seeing the x tied up in here. So my thought is that, okay, let's try and free the x from inside those brackets and see if that helps. Now, right now I'm looking at the fact that we have 3x and an x over here. Just like when you're trying to solve any equation, you want to get those x's together and add them up or subtract or whatever you have to do and get everything else on the other side of the equation. So my next thinking is that I'll bring that 3x across. First I'll bring the minus 1 over here. Then I will bring 3x across. Okay, 3y minus 1, we can't do much with that, but x plus 3x is 4x. Did I make another mistake? Yes, it would be minus xy, my bad. Okay, I think I'm looking forward to our break because I'm starting to make more mistakes now. Here we are, yeah. So minus xy, thank you. Here's a free academic coaching tip. When you're studying, take breaks. When it goes over an hour, your brain will start to just get a bit mushy and you're going to make more mistakes like that. So work in shorter bursts, maybe half hours, maybe 45 minutes if you're able for that. If you're somebody that likes more breaks, go even less. But just don't let your breaks take over and let a 5-minute break turn into a 5-hour break. Definitely take breaks. I've had situations before when I'm trying to solve something, and I'll be just determined that I'm not going to leave until it's solved. I'll spend hours running around with the same thought process, going crazy why it won't work. I get frustrated, and at that point it's time for dinner or something. So I go get dinner. I'll come back to it, and I'll be like, "Oh, it's just this." Just the break can help your mind start to work correct again and get you out of the same kind of cycle of wrong in math anyway. Okay, so what are we trying to do? We're trying to get the x's on their own. So we're bringing the 1 across. We're bringing the xy across. 3y minus 1. Here we're going to factor out the x. Because what we want to do is we want to have x on its own. So we factor out the x and we get, again, common term factoring coming back. And in order to get x on its own, whatever we factored out, we want to just multiply across by that, or sorry, divide across by that, so that it will cancel it and just leave me with x, not x times something. So now I have, again, I'm just going to change the order here, x equals 3y minus 1 over 1 plus y. We now take this step of interchanging. We can call it y equals 3x minus 1 over 1 plus x. And I think if you're looking at another method for doing this, you might see in another text or other instructions online that the very first thing you do is you bring in y equals x. You bring in y instead of f of x. And the very first step is to interchange and to call it x equals y plus 1 over 3 minus y and then solve for y. That's totally acceptable as well. I'm just in the habit of leaving it until the end because sometimes the restriction, it's more convenient working with the restriction when you have it in this form, because the restriction will say x is bigger than something or x is less than something. So it's nicer to have x equals the thing, and then you can say, oh, it has to be this thing because of the restriction. That's why I kind of prefer to do it this way. And then finally, we have f inverse of x equals 3x minus 1 over 1 plus x. And again, a nice thing that you can do is that you can check your answers. So for example, if I plug in x equals 2, what's f of x? F of 2 is going to be 2 plus 1 over 3 minus 2, which is equal to 3 over 1, which is equal to 3. This tells me that if I plug in 3 into the inverse, I should get 2 back out. So f inverse of 3 is going to be 3 times 3 minus 1 over 1 plus 3. That's 9 minus 1 over 4, 8 over 4, which is 2. So you'll notice that f, it took the number 2 and sent it to 3. And f inverse took the number 3 and sent it to 2. So it's doing the job it's supposed to do. It's supposed to, whatever f does to numbers, it's supposed to take the given number and send it back to the original one. Now, of course, I've only just shown that for one single number, so this doesn't prove that it's the inverse. The work we did proved it. This is an example of it working, that's all. Any questions here? Okay. I have 11:26, so I'm going to start again at, sorry, I have 11:16. Do I have time to give you the full 15 minutes or what? I think I do. I think I have time to give you 15 minutes. Yeah, if you've done it correctly, you should be able to, if you plug in, let's say, for example, we plug in 10 and we get 50. Then if you plug in 50 into the inverse, you should get 10 back. So yeah, it should work checking like that, just to see if you've done the right thing. If, for example, if I plugged in 2 and got 3, and then if I plugged in 3 and got 7 or something, I would think, either I've made a mistake in the calculation that led me to get 7 or something, or I've made a mistake in all my work. So yeah, if it doesn't work out like that, if there's a mistake somewhere. Go ahead, Jasmine.
Sorry, I accidentally clicked that.
Okay. Okay, so what we'll do is we'll just take a break now. Let us return at 11:30 and make sure you're back on time, okay? I need to start immediately because this is a little bit longer of a break. Back on time. Okay. Okay, go get some fresh air or get a snack or something if you want. Sure, I'll run through one more of those. But I do have to keep going. I have a lot to do in these classes. Okay, just remind me when we get back. So we're going to start again now. So make sure you're wrapping up whatever you were doing in the break. Okay, so, all right, Lewis wanted to see one more of them. Sure. Actually, Lewis, I'm going to come back to it because just looking again at the textbook, one of the questions is easier to do once we've done composition and quadratics, which also comes today. So if you see questions 7 and 8 in the textbook, I'm going to revisit your question about the plus or minus, because these ones have the restriction. You see x bigger than -2 and x less than 3. Once we've covered composition and quadratics, and transformations, which is the rest of today, hopefully, we'll come back and do one of these examples, and it'll cover what you're looking for as well. Okay. So I'm going to keep going. Actually, why did I do that? I need to keep sharing. Okay, so can you give me a yes in the chat if you've seen composition of functions in high school and are comfortable with it? No? You haven't done composition? Oh, okay. Okay. A few yeses, a few nos. Okay, I'll be going over it anyway, but it's good to know. I'm pretty sure. It's been kind of like that, hasn't it, the last while, with COVID and online learning and stuff. I mean, no, it's not ideal, but that's all we can do. So, okay, composition of functions is basically just like subbing a function into a function. So when you think of like f of x, you imagine subbing in 1, 2, 3, 4 to get numbers out. If you take f of x and you maybe sub in a g of x to get a different function out, that's basically composition of functions. So as an example here, if you can see on the book, let's say you have f of x is 2x and g of x is 3x squared. Let's say you take x and you do g of x to it. So let's say x works on the numbers 1, 2, 3, and so on. If you plug 1 into g of x, you get 3. Because 1 squared is 1 times 3 is 3. If you plug 2 into g of x, 2 squared is 4, 3 4s are 12. If you plug 3 in, 3 squared is 9, 3 9s are 27, and so on. And for any number that you might put in, for example, c, whether it's 5, 6, 7, 8, 9, c, you plug it in and you get 3c squared. Now, the composition part comes in the following bit. It's saying, okay, well, what if you take these resulting numbers and plug them into f? So, for example, if you take this 3 and put it into f of x here, f of 3 would be 2 times 3, which is 6. If you take 12, for example, and plug it into f, 2 times 12 would be 24. If you take 27 and plug it in here, 2 27s are 54. So over here, on this final column over here, that's describing what f of g of x would be. And that's the composition. It's the composition of f and g. So that's really what composition is in a nutshell. There's special notation for it here. There's kind of small circle. F composed with g is just equal to f of g of x. So starting off with some numbers. Let's say we have f of x is 2x cubed and g of x is x plus 4. Suppose we want f composed with g of 1. Well, first we have to find g of 1. Plugging 1 in, you get 1 plus 4, which is 5. And now to get f of g of 1, you plug your g of 1, which was 5, you get f of 5. Now f of x is 2 times x cubed, so 5 cubed is 125. 2 times 125 is 250. Everyone following so far? It's kind of like you take a set of numbers and you might do one function to them, like g, and then with the result of those, you do f to them, and that gets you something new, something else. Now, so far we've only really been looking at numbers. We kind of hinted at composition of functions. So you solve g and then plug the answer for g into f. That's exactly it. Yeah, that's all we've been doing so far. You solve it for g and then plug it into f. Likewise, let's look at number 3 here. 3 was g of f of 0. So this time f is what you do first. So f of 0 is going to be, you plug 0 in here. So f of 0 is just equal to 0. And then you take the result, okay, which was 0, and you plug it into g. So 4 is going to be your answer. Or looking at number 4, for example, f of 2, 2 cubed is 8, 2 times 8 is 16. You plug 16 into g. G of 16 is 20. So this is all it is with numbers, but one thing to note is that if you wanted to skip straight from, for example, 2 to 20, that's a new function. First you're doing f to it, then you're doing g to it. So that gives you a new function. So instead of just looking at what happens to a handful of numbers and saying, oh yeah, with this composition 2 goes to 20 and so on, you can also find new functions from this. So in this example, we had f of x was 2x cubed, g of x was x plus 4, f of g of x well, what does f do to a function? So f of 0, for example, would be 2 times 0 cubed. F of 5 would be 2 times 5 cubed. F of g of x is 2 times g of x cubed. So it's actually going to be 2 times x plus 4 cubed. That is kind of a new function, right? It's not the same as either of the above functions, but it's got from the composition of them. And one thing to note as well is that g of f of x, it doesn't have to be the same as f of g of x. Sometimes it works out the same by coincidence, but it's it can be a different function. So this is g of f of x. What does g do to functions? So over here, just on the side, if you imagine g of x, right? G of 0, 0 plus 4. G of 12 is going to be 12 plus 4. You just take your input and add 4. So here, our input is f of x. We're just going to be adding 4. What was f of x? It was 2x cubed. So 2x cubed plus 4. And you'll note that those are different. This one here is g of f of x. This one is f of g of x. Note that f of g of x is not equal to g of f of x. Sometimes it might be. Might be sometimes equal. But often is not. Okay. That's really all we're doing here. You're gonna want to be comfortable with compositions of functions in calculus, and throughout some extra things we have to do in this course too. But yeah, sometimes they're equal, sometimes they're not. So in here in the text, get it back up again. A couple more examples that you can run through. So, for example, you have f of x, g of x, and also h of x in this problem, and you have some ones to run through here. So f of g of x, what is that? Well, it's just like we did before. F of g of x is root x minus 2. F of root x minus 2, what does f do to functions? It squares them, and then it says minus 7 times that thing. So that's what we're going to do. We're going to take what's inside the brackets here, square it, and then minus 7 times it. Okay. Now, I'm not really interested in simplifying these because all I really want to talk about is the composition here and make sure everyone gets what's going on. You could definitely simplify this. The square root and the squared can cancel, and you can multiply out brackets and things. But in a question about composition, unless I specifically say simplify it in a test or a quiz, I'm really not that interested in seeing the simplification. I just want to know, can you do the composition? Do you know what it is? Okay, g of h of x, for example, h is 1 over x plus 4, so you replace the h of x with 1 over x plus 4. What does g do? It takes the square root of it minus 2. In this case, the it is 1 over x minus 4. So it's the square root of 1 over x minus 4 minus 2. How do we feel about this? Let's do that thing again. Post a number from 1 to 5 in the chat. 1 is, I don't really get it at all. 5 is, this seems fine. And 2, 3, and 4 can be anything in between. How are we feeling? 1, 2, 3, 4, or 5? Bunch of middle of the road stuff. Okay. 5. Spend a little longer then. There's some problems for you here to try. These are just exercises of this section, but what I'll do is run back to my screen that I can write on. I'm gonna do it a little bit more. So you can always read through the text to see those examples in detail again. But what I'll do is I'll do the other kind of variations that weren't covered. This is the textbook. It was problem 3.5.2. We had, what did we have? We had f of x equals x squared minus 7x. G of x is root x minus 2. H of x is 1 over x plus 4. So in the textbook, if you go back to that in your own time, you'll see f of g, g of h, h of f, f of h. There's 2 more variations that I didn't cover, so why don't I just go through these ones and you can read through the textbook ones yourself because the solution is there. G of f was not covered in the textbook, and h of g, I think. Okay, so g of f, you can immediately rewrite this away from that composition notation like this. So the question is, okay, let's change that f of x to this thing up here. That is x squared minus 7x. Now, what does g do to things? It takes the thing inside the bracket, it takes the square root of it and subtracts 2. That's what g of x does. It takes whatever you have in here and just places it right there. That's exactly what we're going to do. We're taking this thing that is inside the brackets and just dropping it in here. These parentheses aren't really necessary, these ones here. That's it. That one okay? Maybe I'll just circle that as well so you can see where it went. Okay. So likewise, this one is going to be similar. H of g of x. What's g of x? Well, that is root x minus 2. And what does h do to things? Well, h takes whatever you put into it, and it does 1 over that thing plus 4. This time what we're putting in is the square root of x minus 2. So that's what's going to go in here. You know what, maybe I'll use a different color here. Okay. You following? Have any of those trees become 4s or 5s yet? 3.5s? Everyone who gave me a number before, give me another number. Wasn't this a little more comfortable? That's more like it. Yeah, so you just want to practice this and make sure that that you feel okay. The 4 becomes a 5 from practice, really. I think everybody should be feeling more like 4 until they've done a bunch themselves and go, okay, that's how these work. Yeah, okay. So composition is mentioned here. It comes up a bit in calculus. You have to do it in certain limit calculations and then certain other calculations as well. We're going to see it a little bit when we do transformations of functions. So you want to have a comfort or an idea of where these functions come from. Kind of a sense of what probably came first and what came later, stuff like that. So that was composition, and I want you to definitely run through all these problems just to make sure you're okay. There's going to be composition problems on the quiz and probably on the assignment as well. They're easy enough, but you just have to run through them and make sure that you're able to do it. So just make sure you get your practice in this for Friday, and in working for the quiz, it'll help you get some study in for the assignment too, and figure out. There's a little bit of overlap between the quiz and the assignment. The assignment covers everything from week 1, what we did factoring, all the way up to the end of this class. And the quiz is only for what we do today. So there's going to be overlap in the quiz and the assignment, and even the midterm. The midterm is going to be quite similar to the assignment. So maybe a little bit easier, not as long because you don't have a week to do it. You only have an hour, so it'll be 5 or 6 questions where you show your work. Okay. Okay, so moving on to transformations of functions, and composition is going to kind of come in here a little bit because the rules for the transformations, they kind of force things to look like a composition of functions in a way. It doesn't get too complicated, but you just kind of want to have an idea of how it works. So by transformations of functions, I mean there's certain changes or perturbations you can do to a given function that will, move it up, move it down, move it left, move it right, stretch it this way, make it taller, flip it over an axis, flip it over a y-axis, things like this. And that's what we're going to be covering in this section, the transformations. Have you seen transformations like that in school? You can give me a yes if you have. Excellent, okay, so this should just be a reminder then. Anybody know? Sorry, touch on it. Okay. Yeah, we're going to touch on it here too, so I should fill in any gaps that you kind of missed in here. Get them. Yeah, we'll go over those ones today then. Okay, so on transformations of functions, I'm going to be using three functions to demonstrate the transformations with. And you can see them here. You have x squared, which looks like this U shape. I'm sure you're all familiar with that one. You have the square root of x, which looks like this. And you also have the absolute value of x, which looks like a V. 45-degree angle kind of for the absolute value of x. 1 second. Sneeze. Okay, so starting off with the shifts. So these are the transformations that shift the function up, down, left, or right. So if you start with a function, and let's say, for example, x squared is the one given here, and you're adding a number to the function on the outside. So you take x squared and you do just +1. That's just going to shift the function directly upwards by 1 unit. If you're taking away a number, so if it's a negative number that's added to the end, if you did f of x minus 1, x squared minus 1 would be like if you take your x squared and everything just gets moved down 1 unit. If you do f of, in brackets here, x plus 1 instead of x, then, or sorry, we're doing it with 2 here, x plus 2, that would shift it 2 units to the left. And if you do it with a negative in here, x minus 2 squared, that would shift it 2 units to the right. So this is just something that we want to learn these rules and know how they're going to change what a function looks like. So I'm going to stop sharing for a second, just do some drawings here, maybe with some of the other functions. So if you remember, originally I told you, for example, that square root of x looks like this. So if you want to draw the square root of x plus 1 like that, what that's going to look like, the transformation the rule that one follows is it's the f of x going to f of x plus c. So that was c units up. Here it's root x becoming root x plus 1. So it's 1 unit up. So what started out as this here, now it's that. So this one here is root x, and this one here is root x plus 1. Okay. Again, if there's something that you're not sure how it corresponds with the rule or something, just ask the question and we can talk about it. One thing you can always do if you want to get a better sense for the rule is plug in a bunch of numbers and see what happens. So for example, let's say if we're graphing root x, right? Let's say you looked at x equals, I'm going to pick numbers that work out nicely here. So 1, 4, 9, 16. Root x would be 1, 2, 3, 4 like this. So let's say we had, okay, I can't really go as far as 16 on this little graph, but let's say that's 1 and that there is 4. That would be 1. And this here would be, this graph is kind of bad. Let me fix it. So let's say I have 1, 2, 3, 4. 1, 2, 3, 4. Okay, the square root of x would look like this. I probably could have started with 0, to be honest. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 was 2. So the graph of root x looks like this. Now, what if I did, which is what we were just doing, right? Root x plus 1. Well, if x is 0, square root of 0 is 0, plus 1 is 1. The square root of 1 is 1, plus 1 is 2. square root of 4 is 2, plus 1 is 3. The square root of 9 is 3, plus 1 is 4. Square root of 16 is 4, plus 1 is 5. So every y value that you're gonna look at, this is like y equals root x or y equals root x plus 1. Every y value has increased by 1, so the graph has just shifted 1 upward. So looking at this one here, 0 got sent to 1, 1 got sent to 2, 4 got sent to 3, and that's as far as we're able to go on the graph, because otherwise I have to go up to 16 or something, or 9. 4 got sent to 3, and all the numbers in between are going to follow that kind of same pattern. That would be root x plus 1. That's why it gets shifted up by 1. You can always just check some numbers to see if it makes sense. But that's kind of how it ends up that way. Okay. Likewise, if we were subtracting 1 over here, it would be coming down by 1. All those numbers, all of these numbers here would be reduced by 1, and we'd be bringing the whole graph down by 1 like that. Okay. So for any of these transformations, if you want to go a little bit deeper, and screen isn't scrolling anymore. What is going on? If you want to go a little bit deeper and try and understand why they change the way they change, it would be a good idea to just plug in some numbers and see what happens to the numbers and try to get a sense for why it's happening that way. Any questions so far? Let's say we have y equals root x, and what we want to draw is y equals root x minus 3. Okay, so this one here, what I'm thinking of is f of x, which is your y of x, becoming f of x minus 3. Now, going back to your set of rules, I'm going to run back to the, where's my, here it is. Going back to my transformations here. For that one that I'm about to try and do, that corresponds to the last rule here, f of x minus c. That shifts the graph c units to the right. And again, you can always run through some numbers if you're not sure how that's going to work. So what's going to happen here then is we started with root x, which looks like this. C units to the right, in this case, is 3 units to the right. 1, 2, 3. That would be root x plus 3. And this kind of makes sense as well, because if you look at this one here, if I asked you what is the domain of root x, you would say x can be bigger than or equal to 0 because I can't take the square root of a negative number. And this would be my domain here. If I ask you what's the domain of, whoops, I've written the wrong function in here. If I asked you what's the domain of root x plus 3, you would say x has to be bigger than or equal to 3 because I can't take the square root of a negative number. So the function starts over there. The domain is all shifted to the right as well. And you have to start from 3. Square root of 0 gives me 0. Square root of 1 gives me 1. Square root of 4 gives me 2. This time, the 0 kind of starts here because it's 3 minus 3 gives you 0. 4. Square root of 4 minus 3 will give me 1. And it's going to be, what gives me 4 inside here? 7, isn't it? 7 minus 3 is 4. So if I go up here to 7, that's what's going to give me 2. So it all gets moved to the right. Okay? Okay, so are there any questions? How is the comfort level on these transformations so far on the shifts? Five on the shifts, excellent, okay. So you can find this little table in the textbook if you want to double check these. Just a quick table of the rules. You should learn them though. You should know them off by heart. Once you practice with them enough, you begin to know them anyway. But if you're not sure, you can always start plugging in numbers and see what happens to a sample function. You could just use x squared or square root of x or something as a sample and see what happens if I make this little change and start plotting the numbers. You go, oh, look, it moved to the right. And just see what happens. Stretching and compressing. So if you take a function f of x and multiply it by a number c that's bigger than 1, so multiply it by like 2, 3, 4, 1.1 even, that's going to stretch away from the x-axis. And if you imagine what's really happening, you're taking a number, let's say the original range element was going to be 4. If you multiply a bigger number, it becomes 8. So it gets higher away from the x-axis. If you multiply it by a number between 0 and 1, like a fraction, you're making it smaller. So it's going to come closer to the x-axis. So this time, the sample function I'm using is the absolute value of x. Remember, the absolute value of x looks like a V shape. If we look at 2 times the absolute value of x, you know, I think I'm just going to draw this. It's in the textbook. You can check it. You can read over it in the textbook at your leisure. I think I want to have the freedom to draw a little bit here. So I'm going to go back here. Let's say, I might just put this on the same graph here. Say I have absolute value of x would look like this. You know, I'm going to make that a little bit smaller. So this is 1, 2, 3, minus 1, minus 2, minus 3. Well, let's just look at the right side here. The absolute value of 1 is 1. The absolute value of 2 is 2, and so on like that. Let's say I wanted to draw the absolute value of 2 times x. Well, if I want to do 2 times the absolute value of x, okay, if I plug in say 0, 2 times 0 is 0. If I plug in 1, 2 times 1 is 2. If I plug in 2, 2 times 2 is 4. If I plug in 3, I get 6. So a number bigger than 1 is going to make all the y values bigger, which means that the function is steeper. It's going to look something more like this on both sides. This would be y equals 2 times the absolute value of x. So 1 becomes 2, 2 becomes 4, and 3 would become 6. So it stretches it upwards, away from the x-axis. Now what would happen if I did, say, a number smaller than 1? Let's say I did half the absolute value of x. Well, half of 0 is still 0. Half of 1 is a half. Half of 2 is 1. Half of 3 is 1.5. So when it's a number smaller than 1, and I multiply it by all those absolute value of x numbers, it's going to be, the y values are going to be smaller, so the graph is going to be pushed down. So it's going to look more like this. Again, 1 becomes a half. It's getting a little hard to see. 2, it's going to be 1. 3 is going to be 1.5. Getting a little bit harder to see, but you get the idea. It gets squished downwards when it's a number smaller than 1. Any questions here? Okay. And the last transformations that we're going to cover. There's more transformations too, but I'm not going to kill you with transformations in this course. The last ones that we're going to do is reflections. So for this one, I'm just going to use the square root of x to demonstrate what would happen with each one. This is about whether or not you multiply by a plus or a minus. So the square root of x, if you remember, it goes roughly the way my mouse is going right now. If you multiply that function by a negative, if f of x goes to a negative f of x, then it flips it over the x-axis. Where did the table go? I don't have a table here. Okay, so I'm missing a table for this part of the textbook. I'm just going to write it in here now. Let me switch back to sharing. So I guess the table that I'm missing there is like this. So just to look like the other ones, change to the function versus the transformation. So let's say we did, you start with f of x and we do minus f of x like that. This would be reflection across the x-axis. And if the change that we make is we do f of minus x like that, that would be a reflection across the y-axis. Looks like I forgot to put that table into the book. Unless I just missed it. No, it looks like I jumped ahead to the example. Okay. So yeah, going back to the, actually maybe I'll just do it here. So the examples that I have in the book there were, if I start with, say, I have x squared done, I have root x done in the book. So I'm going to show you what it would be like for x squared. Let's say I have, here's f of x equals x squared. Let's say what I want to do is I want to change f of x to negative f of x. Well then, it would, this transformation as described in the table above here, it reflects across the x-axis. So what it would look like is like that. That would be f of x equals negative x squared. So x squared goes to negative x squared. This is what it ends up looking like. Now this is kind of a weird example for f of x going to f of negative x, because that looks, if you flip this over the y-axis, it looks the exact same. So I won't talk about that one. Actually, maybe I'll just use a different, that must be why I used root x. So if I do root x here, then this here, oops, that doesn't look great. That there would be the square root of negative x. Okay. Okay. There is a clickable thing here that I put into the notes. I think it should still be working. That I want to show you. There's a website called Desmos, which is very, very handy for graphs. but I've made a thing that you can play with. If this link would ever click, I thought it used to click. It doesn't click anymore. Maybe I need. Okay, I'm just gonna. Can't type it because I have my computer folded over and my keyboard's on the back of my computer. But if this used to click, I think it maybe just bugged out or something. But if you go to this website here, and it's a thing I made where you can adjust sliders and play with transformations to get a better understanding. Actually, I'm gonna try and go through it for a second here. Not click. One second, Desmos.com calculator. Okay, so I'm just going to share a different screen here for a second. So hopefully this is sharing for you now. So what I have here is a function where if you think about what AF of x would be, you can change this and see how the function would change. See how it's stretching away from the x-axis when a gets bigger, and it's going closer to the x-axis when a gets smaller. So it's getting compressed towards the x-axis in that way. So setting that one back to 1. For b, yeah, you can make this one I can't move that slider for some reason. C will move though. So if you look at what happens with C, if you look at the number, if you make C positive, it shifts it directly upwards. It's not being stretched, it's just being shifted straight up. And if you make C negative, it just gets shifted straight down. Okay. F of x plus d. So this is if the d is inside. You can see what happens here. It's being shifted. If d is positive, like +1, +2, +3, it moves to the left. And if you make d negative, it's going to move to the right, like x minus 2, x minus 3, and so on. And f of k times x, this is if you have a number inside. This is not actually a transformation that we're doing, but you can see what happens. It gets either compressed towards the y-axis or away from the y-axis. That's not one we're going to cover, so we'll just leave that one be. Okay. So that's a link that you can click on in the notes just to play around with some of that stuff and see definitely understanding how the transformations and shifts work. Any questions about this? Definitely just pop it in the chat if you have a question. Okay, so those were examples of the transformations kind of done separately. What I'm going to do now is run through some of those transformations when they're all kind of mixed up together. Why is this not showing again? Stop and start again. There we go. Okay, so we kind of looked at them one by one. We looked at the up, down, left, and right shifts. Then we looked at the stretching and the compressing towards or away from the x-axis, and we also looked at the reflections across the x-axis or the y-axis. So putting that all together, oops, let me go black. So putting these transformations together. Let's do some examples where we have to draw what's happening. So sketch f of x equals x minus 1 squared plus 2. G of x equals minus 3 times the absolute value of x plus 1. And h of x, which is 4 minus 2 root x minus 3. And find intercepts where possible. Okay. This is something you might expect to see in an assignment or a midterm, because it's not really something I can ask in a quiz, is it, to sketch something. I could probably show you a picture and then say which of these graphs is, which of these is the picture shown. But this is what a question might look like in a midterm or assignment. Don't bank on that. I mean, I don't remember what I put on the assignment right now or the midterm. I haven't made the midterm yet, so we'll see. Anyway, okay, so let's start off. Okay, so the solution for f of x. What is the kind of parent function for this one? Of those functions that we're playing with, that first function f of x, it looks like transformations of x squared. So what we're thinking is that we're starting with x squared. That there is x squared. Now we want to do transformations so that it becomes x minus 1 squared plus 2. So when I'm looking at this, I'm thinking, okay, I'm going to transform this first so that it becomes x minus 1 squared. What does that do to it? It shifts it 1 unit to the right. This here is x minus 1 squared. Okay? That's one of your transformations that I know you just saw them now. You've seen this before, so you might remember them, but if you haven't seen them or were quite rusty, you might not remember the exact transformation yet. But f of x going to f of x minus 1 means 1 unit to the right. So that's what the first transformation there looks like. The last one then was to go, we did the 1, we're doing the 2 next. We go up by 2. So what does the final thing look like? Well, we went across 1, we're going up by 2. That's what that function now looks like. This is x minus 1 squared plus 2. That is f of x. That's what we were trying to get to. So that is the function that we're looking for. That's how you can use the transformations to sketch that function. You know what x squared looks like, so you know how the movements go. The intercepts, there's no x-intercept as far as we can tell. But what's that y-intercept? How do you find the y-intercept? You're going to set x equal to 0 and see what you get. So y is equal to x minus 1 squared plus 2. Let x equal to 0. So you get y equals 0 minus 1 squared plus 2. Minus 1 squared is 1, which is 3. So the y-intercept is 0, 3. And going back to our little graph up here, 3 is what we get up there. Okay? Any questions there? Okay. Let's go on to the next one. So g of x which was minus 3 times the absolute value of x plus 1. This here, it looks like transformations on the absolute value of x. So that's what we're going to start with. We're going to start with the absolute value of x. Okay, so the first thing that we want to do is do the absolute value of x plus 1. What is that going to look like? Well, if you take an f of x and you change it to f of x plus 1, then that will shift it 1 unit to the left. Okay. Next, let's say we wanted to do 3 times the absolute value of x plus 1. Well, what does that do? If you multiply it by a number bigger than 1, that shifts it, that stretches it away from the x-axis by a factor of 3. So what this originally was, now don't forget, this is minus 1, so we're going to keep track of this. It was at 0, 0 down here. Still at minus 1, but now it's stretched really tall away from the x-axis. Okay. And our final transformation then is the minus sign that's in front of the whole thing. If you remember, that was one of the last ones that we covered. That was a reflection. So that's an f of x going to a negative f of x, which means it's going to reflect over the x-axis. So what it's going to look like now, actually, maybe let me draw this a little bit differently. This is minus 3 times the absolute value of x plus 1. Yeah, that's it. Okay, so that's what the final sketch is going to look like. It looks like we do have a few intercepts. We suspect that this one is minus 1 because it hasn't really changed. We moved it 1 to the left and it went towards minus 1, and then we just we stretched the graph and flipped it. So that minus 1 should be the same, but we can obviously verify that with some algebra. And this here is one that we're not sure about. How do we get the y-intercept? We set x equal to 0, so y, which is minus 3 times the absolute value of x plus 1. For x equal to 0, y equals minus 3 times the absolute value of 1, which is just equal to minus 3. So this one here is at minus 3. Okay. So we have our intercepts, we have our sketch, and we're good to go. One final one, a little more complicated, was h of x equal to 4 minus 2 times the absolute value of x plus 3. Okay, so this looks like transformations on the square root of x. So let's start with the square root of x. Okay, so that's what square root of x looks like to begin with. Now, as you're doing these, you should be kind of working your way from the inside out. So that will be the first step that I take. This minus 2 will be the second step. And finally, I'll add the number in the end for the third step. I find that the easiest way to do it. You start from the inside out and see what you end up with. Okay, so first, I want to turn that root x into root x plus 3. So what happens? It's going to go 3 units to the left. Sorry, I was about to do it to the right. This is going to become root x plus 3. This is going to go all the way over here to minus 3 instead of 0 where it originally started. Okay. Next, we can do 2 times this. All right. So what will 2 times this do? It will stretch it away from the x-axis. So we're still here at -3, but now it's taller. It gets stretched away from the x-axis. And this is 2 times root x plus 3. Next, I mean, I could do this all in one step if I wanted, but next I'm going to do the minus sign. So if I put a minus sign here in front, that's going to flip that over the no, this one actually shifts to the left. It's kind of counterintuitive. You'd think minus would correspond to left and plus would correspond to right. This one actually shifts to the left. X plus number goes to the left, X minus number goes to the right. Yeah, you can check out the table afterwards. It's on my other screen here. Okay, so -2 times root x plus 3. Oh yeah, no worries. You better correct that. It was like this. Now it's like this somehow. So that's still at -3 because all we did is flip it over the x-axis. This is -2 root x plus 3. And finally, we need a 4. So we need a +4 somewhere. So we're going to be shifting it upwards by 4 units. So finally, okay, this was at -3 here. We're going up by 4 units. So let me just keep track of this here. That's 4. That's -3. It's going to look something like this. So this is where the sketch might be a little bit bad, because one thing that I wasn't able to keep track of here was the x-intercept. When I moved it to the left, or sorry, the y-intercept. The y-intercept went somewhere, right? I'm not sure where it went. So I've kind of lost track of the y-intercept immediately because it wasn't totally easy to follow. I also don't know where this y-intercept is, but now I have a problem because this sketch might not be accurate. I don't know if the y-intercept should be above or below the x-axis. So what I need to do is I need to solve it just so that I can definitely draw an accurate sketch. So this is one that I'm going to draw another sketch to make sure. Oh, and as well, I also don't know where this is. I also don't know this. Because when I shifted it upwards, somewhere, something here ended up turning into that, and I don't know what exactly it was, or how far it is over. So that's something else that I have to try and figure out too. So the intercepts are definitely needed this time. In the other ones we did, we could kind of keep track of where the intercepts went, maybe except for the y-intercept once or twice. So for the x-intercept, what was our function? It was 4 minus 2 root x plus 3, I think. Yeah. So this is like this final, I never wrote down the function. This final one was minus 2 root x plus 3. You can do it as +4 here, or you can put the 4 on the other side of it. It doesn't matter where you put the 4. So the x-intercept, again, we're going to set y equal to 0. So 0 is equal to 4 minus 2 root x plus 3, and we solve. Bring the 4 across. Actually, let's bring the other stuff across. Let's bring the 2 root x plus 3 across. So root x plus 3, if we divide across by 2, now we want to solve for that x, so we're going to square both sides. We get x equals -1. Okay, so it actually was a nice number. X equals -1 is the answer we got for the x-intercept. So it's 1, 0. And for the y-intercept, we're going to set x equal to 0. So y is 4 minus 2 root x plus 3. So it's 4 minus 2 root 0 plus 3. This won't be a very nice number. 2 root 3. Root 3 is about 1.7. I think. Something like that. So this is roughly equal to 4 minus 2 times 1.7. Hope I'm not wrong about that. Which is 4 minus something like 3.4, which is 0.6. So the y-intercept should be 0 and 0.6. So I did have it wrong. If you look back here, I had the y-intercept being negative. That was inaccurate because what we've just worked out is the y-intercept is a positive number, 0.6, just above the x-axis. So a better sketch. Minus 1, minus 2, minus 3, minus 4. 1, 2, 3, 4. So this was where it started. We tracked it all the way up to minus 3, 4. It has, what was it? It had an x-intercept at oh look, I have negative 1 here. That should have been positive 1. 4 minus 3 is positive 1. An x-intercept at 1, 0. Here's an x-intercept. The y-intercept was 0.6, so it's about here. Now we're definitely doing a better sketch now. That's better. That's what we're after. So this is the function. Oh, sorry, I think it was called h of x, wasn't it? H of x is 4 minus 2 root x plus 3. Okay. Any questions here? Just more transformations, except we had some x-intercepts and y-intercepts attached to the end to make sure that the sketch was good. How do you feel with this one? Maybe I'll give you one more piece of info about this. If you have any questions, do write it in the chat now. I'm just going to write one more piece of info here. Think of a rule for sketching transformations. Start from the inside and work your way out. You can often get away with not really following this rule exactly. So for example, if you have f of x being transformed into something like a times f of x plus b, for example, plus c, you should start in here, do that first, do that second, and do that third. Okay. There's not many cases where it matters. I think there's a few functions where if you do one thing in an order before the other one, it'll get messed up. Yeah, I think maybe if you do step 2 before 3, or step 3 before you do step 2, it might get messed up. But just as a general rule, think of it that way. Okay. I'm going to move on to the last topic for today. So we're going to be putting a lot of this together, the compositions, the sketching, not so much the inverses, I guess, but putting all that stuff together into quadratic equations. So this should be a comfortable end to the class. You should be okay with this stuff, I think. It's just a nice topic to kind of wrap it all up. Yeah, so lots of exercises to transform here. Quadratic functions. Okay, so you probably know this, but if you see a function, a quadratic function like ax squared plus bx plus c, it's going to have some kind of a u shape, or maybe possibly an n shape like this. That would be if the coefficient in front of the x squared is negative. It might be narrow, it might be wide. It depends on the A, B, and C. And if the A part is negative, it'll be kind of upside down like this. So throughout your kind of school years, as you've been doing, as you've been working with quadratics, you're going to see, if you've ever been drawing them, you'll see a lot of U-shaped things, or maybe they're upside down, stuff like that. Something that you're probably okay with. What was I mentioning here? U-shape or N-shape. Yeah, if the A is negative, it's going to be N-shape. The steepness can vary depending on the values of the A, B, and C, in particular the value of A. And the graph may or may not intersect the x-axis. So here it had 2 interceptions. Here it only touched it once. Here it didn't touch it at all. Here it had 2 as well. It touches the x-axis twice. A couple of options there. Moving on to finding roots of quadratic equations then. So a quadratic function is just when it's like f of x equals some function like this. The quadratic equation is when it's set equal to 0 and you're maybe trying to solve or do stuff with it like that. Let's look at a quick example. X squared plus 2x minus 3. This one has roots at -3 and 1, because if you plug those in, you get 0, and those are the x-intercepts. There's ways that you can find roots of quadratic equations. The first way that you should always come to mind is factoring. Factoring should always be the first thing that you try. For example, if you have x squared minus 4x minus 5, well, remember how we did factoring in the very first class? You can factor that into x minus 5 times x plus 1. And then you set each factor equal to 0 individually and solve to get the roots. Likewise, you had the other factoring technique where if it wasn't just the 1 times x squared, if it was something else, you had to say, oh, well, 4 times 2 is 8. Negative 2 is negative 8. I need numbers multiplying to negative 8 that add to make negative 7. That's negative 8 and 1. And then you do factor by grouping. And you can solve the roots that way. Again, by setting each of the factors equal to 0. So hopefully this is ringing a loud bell for everybody, and you're comfortable enough with the quadratic equations and factoring to solve them. Notice that, oh yeah, one thing to point out is that whenever you're going to set factors equal to the right-hand side always has to be 0. If you had a 1 over here, you can't solve. It has to be 0 on the right side in order for you to solve these. Make sure that you read through this part carefully just to get the explanation again if you're a bit rusty. Another way to solve quadratic equations is to do the quadratic formula. This is one that you should have memorized. X equals minus b plus minus the square root of b squared minus 4ac over 2a. Here's an example of using the quadratic formula. Your a is 4, your b is minus 7, and your c is minus 3. You just plug those numbers into the formula, multiply the numbers out, add them up, square things, and so on, and you get your solutions. And this leads us on to the discriminant. The thing inside the square root here, the b squared minus 4ac, gets a special name, and it's called the discriminant, because just the value of the discriminant tells you whether or not there is 0 solutions, 1 solution, or 2 solutions to a quadratic equation. If the discriminant is 0, there's 1 real solution. If it's positive, there's 2 real solutions. And if it's negative, there are no real solutions. So I want to double check. I've been skipping through this pretty fast. Everybody comfortable with this? Give me your 5s or your 1s or 3s or whatever, please. Just type into the chat. You're all fine with this? Okay, that's good to see. I'll keep going. Have you seen a good few 4s? You normally write 5, so just wondering, which part of it is that's making you hang back and say 4? Is it the discriminant? Is that a term you heard from high school? Have you done the discriminant before? Have. Okay, that's good. Perfect, okay. Yeah, it's just a quick way. It's like isolating. Bit rusty. Yeah, you'll get the practice. You'll definitely get the practice in. The discriminant really is just isolating that one part of the quadratic formula, and you'll notice that where the 0, 1, or 2 solutions comes from. If you have a negative under the square root, this thing isn't defined at all, and you have no answers because the thing is undefined. That's why you get no solutions if it's negative underneath the square root. If the thing inside the square root is 0, then what would have been 2 answers, the plus or minus, it's plus or minus 0. So your only answer is just minus b over 2a because the other thing is 0. So therefore 1 solution. And if this is positive, then you get 2 solutions because you have the plus option or the minus option. That's really where the 0, 1, or 2 comes from. And a final way that you can solve quadratics is by completing the square. Will I do this now or not? Let me just check what we have to do next week. Next week we're solving polynomials, rational and absolute values. That's quite a bit to do next week. Yeah, we'll finish this off today. I was looking for an excuse to end class early, to be honest. I'm a little tired. I think you guys are too. Okay. So, completing the square. So if you take a quadratic equation and you can rearrange it into this kind of form here, you can also solve it by saying that x plus a can be either positive root b or negative root b. And then you can bring the a across and solve for x in both cases. It's another way to solve a quadratic. So, for example, say you're trying to solve x squared minus 3x plus 1. What you can do if you're using this method of completing the square, you want to rearrange this into this kind of form here. X plus a squared equals b. How you do it is you bring the number across, the minus 1. You take this number here, the negative 3, that is multiplying by the x. You divide it by 2 and then square it. So you're going to be adding that number to both sides of the equation. And you do that because the left side factors perfectly if you do that. It factors into x minus 3 over 2 squared. And then you can get the solutions. You can say if x minus 3 over 2 squared is going to be 5 over 4, then this thing inside the power of 2, that's either plus root 5 over 4 or negative root 5 over 4. And with those two equations separated, you just bring the number across and solve for x. It's another way to solve quadratic equations. I'm going to run through an example of that separately here with the pen because it's a little hard to just kind of read all that out. I'm going to do one live. Oh, here's one done. A little separate. Yes, this is sketching. So I'm just reading ahead of it here. I'm a little tired. Sketch the function. What's my question? Okay. I think I need to be doing something to rather than just reading to teach this effectively. So I'm going to switch and go back to the screen. Okay. So what I'm going to do is run through one quadratic equation where I'm going to do kind of everything with it, okay? This will kind of sum up what's in that textbook. And I want you to definitely read through that a couple of times from completing the square onwards because it's kind of, it's a little heavier than the other stuff, so you want to just put in your time on this. But what I'm going to do is take one example of a quadratic function and do everything that I want to do with it. The factoring, quadratic equation, completing the square, sketching, domain and range, all that stuff that you'll find in the textbook that I want you to definitely read through in your own time. I'm going to do it to this particular example here. Okay, so here are my questions. Factor and solve. Use the quadratic equation and solve. Sorry, the quadratic formula. Complete the square and solve. So we're going to solve this every possible way. With all this information, I'm going to use a variation of the complete the square method to sketch. And we're going to talk about what is domain and range. That's what we're going to answer for this problem here. Okay, so the first three questions that we do, the first three, we're going to get the same answer because we're just trying to solve for x in each one. Solve equal to 0. I should say solve it equal to 0 for each one. Okay, so the first one is factoring. We had x squared minus 6x plus 5 equal to 0. Okay, this is one that we can just factor like so. So numbers that multiply to make positive 5 and add to make negative 6 are minus 5 and minus 1. So we can say x minus 5 equals 0, x minus 1 equals 0. So x equals 5, x equals 1. That's the solution to f of x equals 0. And one thing I'll note is that these are the x-intercepts of the function f of x equals x squared minus 6x plus 5. To get the x-intercepts, you remember, you let it equal to y, you set y equal to 0 and you solve. That's exactly what we did right there. So they're the roots of the function as well. The other option was the quadratic formula. Remember, that one is minus b plus or minus the square root of b squared minus 4ac over 2a. So sometimes factoring won't work. It's kind of hard to factor and you have nasty answers and stuff. Quadratic formula can always be used if that doesn't work. Factoring did work in the first case, so you wouldn't really have to do this, but this is just to kind of run through everything. What did we have in this? We have a equals 1, b equals minus 6, and c equals 5. So let's plug in all those numbers. Minus negative 6 plus or minus the square root of minus 6 squared minus 4 by 1 by 5. All divided by 2 times 1. This is 6 plus or minus the square root. I'm going to skip some of the multiplication here. Minus 6 squared is 36. 4 5s are 20. 36 minus 20 is 16. So this is the square root of 16 over 2, which is 6 plus or minus 4 over 2. So our answers, x equals 6 plus 4 over 2, x equals 6 minus 4 over 2. Those are the two answers. 10 over 2, sorry, I'm thinking ahead. 10 over 2, which is 5, and 2 over 2, which is 1. So 5 and 1 are what we get when we solve these. Same as before. We got 5 and 1 in the first method too. That's what we expected. For completing the square, we have x squared minus 5x plus 6 equal to 0. How we do this? I ran through it briefly in the textbook there. We bring the 6 across. Wait, sorry, I've written it down wrong, haven't I? Yes, it was minus 6x plus 5, my bad. Minus 6x plus 5. So we bring the 5 across. This number that multiplies by the 6, by the x, sorry. You take that number, divide it by 2, and then square it. Okay, that's part of the method for completing the square. And what we do is we add that to both sides. We do this because when we factor this side, it always turns into a perfect square. So numbers that add to make -6 and multiply to make 9 are -3 and -3. And over here we have 4. So this is x minus 3 squared equals 4. Now this is what we wanted. We wanted it in the form x plus a squared equals b, like that. So here's how completing the square works. We say then that x minus 3 can be positive root 4, or x minus 3 can be negative root 4. So x minus 3 is 2, x minus 3 is negative 2. So x is 5, or x is 1, just like we got before, 5 and 1. So 3 different methods to solve the quadratic equation. Any questions so far? They should all feel fairly comfortable, I guess, because you did quadratics before. You definitely did them in high school. So that's the first 3 done. We factored it and solved. We used the quadratic formula to solve. And we also completed the square to solve. So question 4 is 4 and 5 are a little different. They're back to sketching here. So use complete the square to sketch. So what we're going to use is actually a variation on that complete the square method to sketch. We have f of x was x squared minus 6x plus 5. In a quiz, would you ask to use a specific method? I haven't finished your quiz for this week, so I haven't thought through the possibilities of what I could and couldn't put on the quiz. I'm a bit limited by the quiz because the software that we have on Canvas for quizzes is a little bit limited for maths courses. So I can do multiple choice, multi-select, I can make you fill in the blanks and stuff. I guess it's possible. I could probably come up with some kind of fill in the blank question where you would it would look like completing the square or a quadratic formula or something. It's possible. It's possible. I wouldn't rule it out. So yeah, you want to know all these. Okay. Where was I? Oh yeah, we're going to use a variation on completing the square. So in order to sketch this, okay, what we want in the end is we want this to look like, we want to transform this into something like x plus a squared plus b somehow, right? Because what we can do to sketch it then is we can say, oh, well, we can just use what we know about transformations to shift it and then shift it again. So we want to rearrange this into this in order to sketch. So what's that going to look like? It looks like a variation of the completing the square method. Okay. So we'll take that minus 6 again, divide it by 2 and square it to get 9. Now, the reason I want that is I want my f of x, which is x squared minus 6x plus 5, just like in completing the square before, that x squared, if that was a 9 instead of a 5 or whatever it is, I can get that into the form that I want it. So what I'm going to do is I'm going to say that this needs to be x squared minus 6x plus 9, but I can't just go ahead and change that 5 to a 9. It has to still add up to 5 in total, so I have to subtract the 4. Okay? The reason I wanted to do this is because this here can be factored into that. Okay. Everyone with me? This is something that I can sketch because this looks like transformations on x squared. This looks like transformations of x squared. So let's see what it looks like. If x squared starts like this, next up would be x minus 3 squared, so that's going to shift it to the right. Over to 3. This is x squared, this would be x minus 3 squared. And then finally, down by 4, we'll bring it down to here. Oops, that's kind of a bad line. This here would be x minus 3 squared minus 4. Now, I wonder, can you guess what the intercepts are? We only solved them 3 times, right? We were thinking 1 and 5. So it kind of fits, right? It's sort of centered around 3 here. It went down a bunch, it goes through 1 and it goes through 5. Okay. So better sketch. We got a sense for where it went. Let me just draw it out properly here. 1, 2, 3, 4, 5. Minus 1, minus 2, minus 3, minus 4. We found that the base of it went there. It went up through 1, and it's going to go through the y-axis somewhere. We should probably solve that too. This is going through 5 and there. What's the y-intercept? What was our function? It was f of x equals x squared minus 6x plus 5. If we let x equal to 0, then y is 0 squared minus 6 times 0 plus 5. So it's equal to 5. So that there is 5. Okay. Any questions? This kind of ties everything together. We were talking about sketching, transformations, quadratics, completing the square, intercepts. I like this kind of question. It kind of brings everything together. So I would say expect something like this on quiz or midterm. Go up to the first variation of the completing the square. Yep. Was there a line that you weren't sure about, or? Feel free to unmute if it's awkward to type out your whole question.
Yeah, I'm just wondering if like it will always be for example, minus 6 over 2, like that that 2 under will always be 2, right?
Yes, yeah. Whatever number is multiplying by the x, you divide that by 2 and square it, and that's the number that you want on that side of the equation. Okay. So if we had an x squared minus a 12x plus 19 or whatever it might be, you take the minus 12, divide it by 2, and you get minus 6, and square the 6 is going to be 36. So it would be like x squared minus 12x plus 36, and it would be x minus 6 squared. Sorry, that's a bit messy. I ran out of space. Actually, let me do that one more time on somewhere with a little bit more space. One more example of completing the square. Let's say we have, what was it I used? X squared minus 12x plus 19. You take the 12, divided by 2 to get -6. That's going to be the key number that's going to come out in the as the root. -6 squared is 36. So this is going to be x squared minus 12x. I need that to be a 36 there. So 19 has to be written as 36 minus 17. I think 17 and 19 is 36. And that there is going to be x minus 6 squared minus 17. Okay. So yeah, you always take the number in front of the x term, divide it by 2 to get whatever this is. That is always going to be the number, that number that you get when you divide by 2 is always going to be the one that ends up here. You have to square it because that's the number that you need in order for it to work. And you have to modify that number using this one that you just found. So you have to write it as 36 minus something. Turns out that something was -17 in order for it to work. Okay. All right, we'll stop there. I never got to the question that you asked originally, Lewis, so I'm going to do that at the start of the next class because we're going 2 minutes over time. That's going back to those inverse questions. So it's going to be something like this. You're going to go, when you're trying to find the inverse, you have to complete the square and then isolate the x. So you're going to, for example, you would bring the 17 across the equal sign, take the square root and so on. So it kind of uses this method to solve that. But we'll do it, I'll run back to it and do it at the start of the next class, okay? Just ran out of time today. Okay, so anybody who has me for coaching, I'll see you at 2 p.m. This time the link should be correct. There was a lot of confusion last week. And I'll see you then. Go get a snack or take a break or something. I'm definitely going to take a break. I'm tired. And I'll see you at 2 o'clock. Okay, so yeah, you can find the link on the coaching Canvas page. It should be correct this time. So I'll see you then. Okay, take care, everyone. And see you soon. Stop the recording.